कुठं वरती Okay, welcome back to the class. Can you hear me?
Yes, sir.
Okay. So in previous class, I told you I will give you complete derivation. See here, this is the first derivation, which we have done in a shortcut by missing out some steps in previous class. Here it is a complete derivation. You can see the first order system for unit step input. So R of t, you can see the graph, the flat line, that is R of t, which is written on that. Unit step input means its value is 1 only. I have taken all unit. If the gain of the system is also 1, whereas the step input is also 1. So if it is more, then you have to simply multiply by that factor. Gain and the size of the step gets multiplied. Suppose the k is the gain of the system and a is the size of the step. So then everything gets multiplied by a and k. The equation gets multiplied by a and k. Suppose k is 2 and a is 3. So everything gets multiplied by 2 into 3, that is 6. So that is understood. So I have left out those constants here for derivation for simplicity. So here you can see this is the signal versus time graph. The input signal and output signal are plotted on the same graph. I am showing it. So instead of drawing two separate graphs, I have drawn only one graph. So R of t, you can see this is a horizontal line, that is a step input. And it is unit step input. 1 is written in front of that, means it is value is 1 unit. So here for time t equal to 0, it is 0. For time t greater than 0, it is 1. So here R of t is written as 1 and R of s, after taking a Laplace transform, it is 1 upon s. So here this is our standard first order system. The standard first order system CS by RS, that is output divided by input, transfer function is 1 upon TS plus 1. 1 I have taken. It can be K divided by TS plus 1, where K is the gain of the system. So K is 1 in our case. So I have taken everything in terms of 1 only. So now what I will take is C of S is equal to this multiplied by R of S. I am now substituting the value of R of S, that is 1 upon S. So here now the transfer output is C of S is 1 upon TS plus 1 into 1 upon S. Now this output I want to plot, but this output at present is in the form of a Laplace transform because S is there. So naturally you cannot plot it. So you have to plot, that has to be brought into the real case, that is C of t in form of C output versus time. So to bring it, this is not a standard Laplace. So first you have to bring it into a standard Laplace so that you can take a inverse Laplace. So for that purpose, I will use the partial fractions method. So this is one term 1 upon TS plus 1 and this is another term 1 upon S. So 1 upon S into TS plus 1, this is a multiplication, is equal to A divided by S plus B divided by TS plus 1. This A and B are partial fractions. So first I will separate them so that they can be brought into a standard form so that you can take the inverse Laplace. So multiplying both sides of the by denominator of A. What is denominator? I am evaluating the A first. To evaluate A, what you have to do is multiply both sides of the equation by denominator of A. If you multiply both sides of the equation by denominator of A, left hand side S upon S both cancels, 1 upon TS plus 1 remains. A upon S multiplied by S, A will remain. and b into s divided by ts plus 1. So by doing this, what you achieve is there is no s in a. So that if you take now limit s tending to 0, that is denominator of a tending to 0 by which you have multiplied. So if you take that tending to 0, if s tends to 0, this is 1 upon s is 0 means t into s is 0 plus 1. 1 upon 1 is 1 on the left hand side. Whereas a is as it is. Here b into s is there. So b into 0 is 0. So this will vanish. So the value of a is 1. This is how the partial fractions are determined. Now, similarly, if you want to determine the partial fraction b in the main equation. So to evaluate b, you have to multiply both sides of the equation by denominator of b. I will multiply by denominator of b, that is 1 plus ts or ts plus 1. So if you multiply ts plus 1 on the left hand side, this ts plus 1 and this ts plus 1 cancels. Only s remains. 1 upon s will remain here. A into ts plus 1 upon s, b into ts plus 1 divided by ts plus 1 cancels. So b only will remain. So now see, b doesn't contain any s. Now take limit denominator of b tending to 0, that is by which you have multiplied, that is ts plus 1 tending to 0. So ts plus 1 tending to 0 means ts is tending to minus 1. So that is s is tending to minus 1 upon t. Substitute wherever there is s minus 1 upon t. I will substitute it by 1 upon minus 1 upon t is the t comes into the numerator with the minus sign. B is minus t. Now I will substitute that. 1 a is 1 upon s, b is minus t upon ts plus 1. This is in standard form. If you take the inverse Laplace now, this becomes c of t, c of s will become c of t, and 1 upon s becomes 1, and minus t divided by ts plus 1, minus t sign becomes, this sign becomes minus, and t divided by ts plus 1 is a standard form only, that is e to the power minus t by t. So if you see the graph here, it is exponential graph rising like that. See, as a time t goes on increasing, as small time t goes on increasing, e to the power anything with the minus value goes on decreasing. So e to the power minus t by t goes on decreasing. So we will slowly approach equal to 1. That is equal to our r of t, that is input. This is what is the derivation for first order system for unit step input. Is it clear now? More clearer than that cannot be done. Is it clear?
Yes, sir.
No. So similarly, I will do it for unit ramp function also. This is for unit ramp signal. First order system subjected to unit ramp input. Why I am giving this is sometimes these derivations are also asked, and in no book complete derivation is done, because they will not do it by partial fractions. They will just show how to get that result. So here I am supplying this with unit ramp function. Unit ramp function is straight line. You can see this top straight line is unit ramp function. Unit because the slope of this line is 1 unit. That means angle is 45 degrees. So r of t is t and r of s is 1 upon s square, that we have seen in the previous class. So now instead of any magnitude, it is 1. It is 1t actually. 1t. R of t is 1t. That is slope is 1. So r of s is 1 upon s square. Now cs by rs is our standard transfer function of first order system, 1 upon ts plus 1, where r of s I will take it on other side, so that becomes r of s into 1 upon ts plus 1 is cs. So r of s value I will substitute 1 upon s square, and this one is 1 upon ts plus 1. So now this is not in a standard form. To bring it into a standard form, I will write the partial fractions. That is 1 upon s square plus ts plus 1 can be written as a upon s square. When the s square or s cube term will be there will be additional partial fractions. So a upon s square, then b upon s also has to be considered. If it is s cube, for unit parabolic function, it is s cube. So in that case, you will get one term a upon s cube, b upon s square, c upon s. 3 terms you will get. Now here s square means there are 2 terms corresponding to s square, that is a upon s square and b upon s. Then c upon ts plus 1 as it is. C upon ts plus 1 as it is. Now to evaluate a, just similar to the previous case, multiply both sides of the equation by denominator of the a, that is s square. So if you multiply by s square, this s square will vanish. So 1 upon ts plus 1 will remain in the left hand side. A upon s square cancels. So only a will remain. Then b into s square divided by s, bs will remain. Then c into s square divided by ts plus 1 will remain. Now take s square tending to 0 or s tending to 0. If you take s tending to 0, this becomes 1. Left hand side becomes 1. Only a is there. This becomes 0. C also becomes 0. So you have evaluated a. For b, you cannot follow this procedure because what is denominator of b is s. So if you multiply both sides of the equation, here one s will remain, here also one s will remain. And if you take s tending to 0, this part will become infinity and this part will also become infinity. So you cannot evaluate b like that. So to evaluate b, you have to follow the similar procedure of a. That means multiply both sides of the equation by s square, then differentiate that, d by ds. So left hand side, if you multiply both sides of the equation by s square, only ts 1 upon ts plus 1 will remain. Differentiate that. 1 upon ts plus 1 can be written as ts plus 1 raised to minus 1. And now you differentiate this. So differentiation of minus 1 plus ts raised to minus 1 is minus t. It is differentiation with respect to s only. So this t will remain, t raised to minus 1, that is minus sign will be there. And whereas, so b will become equal to minus t. For c, same procedure, multiply by both sides by denominator of c, that is ts plus 1. 1 upon s square will remain on left hand side. A will vanish, b will vanish, c will be only possible. And now you have to substitute denominator of c tending to 0, that is ts plus 1 tending to 0, not s tending to 0. So s is tending to, ts is tending to minus 1 or s is tending to minus 1 upon t. Wherever there is s is there, you substitute it by 1 upon t. So this minus 1 upon t, if you substitute, minus of my square is there, that minus sign will vanish. 1 upon t square will be there, that t square goes to numerator. So c will be equal to t square. Now 1 upon s square into ts plus 1 can be written as a upon s square, that is 1 upon s square, a value is 1, b upon s, that is minus t upon s, and c upon s, that is ts plus 1, that is t square into ts plus 1. These are all are in standard form. 1 upon s square inverse Laplace is t. Say Laplace transform of t is 1 upon s square. So inverse Laplace of t is 1 upon s square is t. So t upon s is 1 upon s into t. So 1 upon s inverse Laplace is 1. So t will remain as it is. So minus t, and t square divided by ts plus 1 can be written as t into t divided by ts plus 1. T divided by ts plus 1 is e to the power minus t by tau t, whereas 1 t will remain. So the coefficient will become t, and e to the power minus t by 2 out of t square, 1 t will vanish along with that. Yes. Yes. So this only we have done previously, and then you can write this solution in terms of this. This can be simplified like this. This is the output c of t for unit ramp function. So the output you can see here, it continuously lags behind the input. It will continuously lag behind the input, and the gap between the two is equal to time constant of the system, capital T. This is the second derivation. For impulse response, derivation is very simple. This is a impulse response. This square, this rectangle, whatever is there, that is called as delta t. It is a force of input of large magnitude acting for a very short duration of a time. So very short duration of time, delta t, it is acting. So R of t is represented as delta t. And if you take a Laplace transform of R of delta t, it is 1. So now output C of S divided by R of S is 1 upon Ts plus 1. So R of S is 1 here, and this 1 upon Ts plus 1, only 1 upon Ts plus 1. Inverse Laplace of that is directly available. 1 T is missing, so it is 1 upon T into e to the power minus T by T. Not minus sign, it is plus sign only by mistake. It is not a minus sign, it is scratch mark. So these are the three derivations which are commonly asked in the first order system. Do you have any, now have you understood this? You have any difficulty? It says unmute your mic and tell me so that I can move forward. Two people are there. Okay. Now we'll go to second order system. A second order system will consist of a square term. Second order system will consist of a square term. So here you can see here, suppose this is our second order system. Spring mass damper system. There is a mass here, there is a K here, spring, there is a damping ratio B is there, it is acted upon by F of t, so the displacement is X of t. Now this simple type of system you have solved number of times, so I directly write the F of S is equal to ms square into X of S plus Bs into X of S into K into X of S. That is m d square x by dt square plus b dx by dt plus k into x of t. If you take a Laplace transform, f of t becomes f of s, m s square x of s it will become, because m d square x by dt square is there. Similarly, b into dx by dt is there, so bs into x of s and k into x of s it will become. So from this you can take f of s is equal to k x of s common, ms square plus bf plus k. So the transfer function is output, that is x, displacement, input, that is force F, that is cs upon rs, is equal to k divided by ms square plus bs plus k. So this k is the gain of the system I have taken additionally, not there in this. Actually it is 1 upon ms square plus bs plus k, so that 1 can be anything. Instead of 1, it can be taken as gain, k, in general. Now, it has to be brought into standard form. This equation has to be brought into standard form, means highest power of S should not consist of any coefficient other than 1. So, but here the coefficient of S square is m. I don't want m. So, I will multiply and divide the denominator by m. Multiply and divide the whole equation by m. So it will become k upon m in the numerator. Then s square into m divided by m is s square. B upon m into s and k upon m as it is. Now I will put, you know, what is natural frequency of vibration for spring mass system? It is root k by m. So omega n is root k by m, or k by m is equal to omega n square. That I have put. Similarly, b upon m is equal to 2 zeta omega n. I will come directly. I will not go into much details about it. So because you have already completed your vibration course. So where zeta is damping ratio, and b upon m, if I put it as 2 zeta omega n, then this whole equation becomes Cs upon Rs is equal to omega n square into s square divided by s square plus 2 zeta omega n plus omega n square. This is what is the system equation. Now, if you consider the denominator of this equation, that is s square plus 2 zeta omega n into s plus omega n square, this is a second order equation. So it will have two roots. The two roots are found out by minus b plus or minus under root of b square minus 4ac formula. Minus b is minus 2 zeta omega n. I am finding out the roots of s. So this is s square term is there. So the two roots are minus b, that is minus 2 zeta omega n plus or minus under root of b square minus 4ac. B square is 2 zeta omega n whole square, that is 4 zeta square omega n square, minus 4ac, that is 4 into 1 into omega n square, that is 4 omega n square, divided by 2a, that is 2 into 1. So if you simplify this, it will become this 2, this 4 I can take it out. So when it comes out of the root, it will become 2. This 2 cancels, this 2 cancels. Then it will become minus zeta omega n plus or minus omega n square also I can take common. So if it comes out of the root, it will become omega n root of zeta square minus 1. This is possible if the zeta is greater than 1. If the zeta, that is called as damping ratio, greater than 1, this is what is the equation. But there are three possibilities now. When zeta is greater than 1, zeta equal to 1, and zeta equal to less than 1. If zeta is greater than 1, this equation is there, that is minus zeta omega n plus or minus omega n into root of zeta square minus 1. If zeta is equal to 1, in the same equation I will put zeta is equal to 1. If the zeta is equal to 1 means zeta will vanish. So this 1, that will only omega n will remain. Here zeta is 1, zeta square is also 1, 1 minus 1 is 0, root of 0 is vanishes. So this root of 0 is 0, 0 into omega n will be 0. In that case, both the roots are plus or minus omega n only, minus omega n only, sorry. That is this part, the real part only. The third case is zeta less than 1. If zeta is less than 1, zeta square will be still smaller. When zeta square is still smaller, that smaller than 1, then that will be negative quantity. Under root of negative quantity does not exist, that is, it is imaginary. So if I take root of minus 1 as a j, in that case, I will take that minus sign out. So it will become 1 minus zeta square. So it will become 1 minus zeta square because I have taken minus sign outside. Root of minus 1 is j, that is imaginary. So the two roots are minus zeta omega n plus or minus omega n into root of 1 minus zeta square. So here it is zeta square minus 1. Now I have taken minus sign outside. So it becomes 1 minus zeta square inside, and root of minus 1 is imaginary quantity j or I. So this is what is the equation now. Now here there are three different cases: under damped case, critically damped case, or over damped case. Under damped case is when zeta is less than 1. The roots are like this, that is minus zeta omega n plus or minus omega n into root of 1 minus zeta square. That is, this is under damped case. Then critically damped case, both the roots are real and same, that is minus omega n. And the third case is that greater than 1, that is over damped case. In that case, the roots are minus zeta omega n plus or minus omega n into zeta square minus 1. Is it okay? So now in first order system, as there was only one root, there were only three derivations we have done. What are the three derivations? One subjected to step input, one subjected to ramp input, and one subjected to impulse input. I have not done parabolic input. But here what happens is there are two roots and three possibilities. Three possibilities is under damp, critically damped, and over damped. So 3 into 3, total 9 derivations will come. It is not possible to do all the 9 derivations, and it is not required also. The procedure remains same. So for that purpose, I have done only for underdamped case, which is most commonly used in most of the cases. So this is the underdamped case. Now you can subject that underdamped system to either step input or a ramp input or impulse input. Now ramp input also and impulse input also not very commonly used. Step input is most important for a second order system, and that too underdamped system is most important. So we'll only concentrate on that, but that doesn't mean that other things are not there. You have to just go through that, and on the similar grounds you have to practice. So if you have any questions, you stop, you ask. Otherwise, I will stop now for half an hour break up to 11 o'clock, and then I will start the derivation. Up to, sorry, not 11 o'clock, 1 o'clock. I'm used to that 10 to 12 class. So I'm saying that timing is 1 o'clock. Any questions are there?